for question number 1, we need to show that the function square root x on 0 to positive infinity is uniformly continuous but does not satisfy the Lipschitz conditions. So first of all, we have the epsilon more than 0, and then we let the delta is equal to epsilon square. And then we have the modulus x minus y must be less than the delta, where the x and y more and equal to 0. And then we need to estimate the modulus function x minus function y, which is xy is element of 0 and delta, and then the modulus function x minus function y will be less than the function delta minus f0, and then this will equal to square root delta, and then we change the value of delta equal to epsilon square, and then we will get the square root of epsilon square, which is equal to epsilon. Otherwise, when x is not element of 0 and delta, or y is not element of 0 and delta, we will have the maximum xy is more and equal to delta. Then the modulus square root x minus square root y will get x minus y over the square root x plus square root y, which is less than equal to only modulus x minus y over the square root maximum xy, which is it will less delta over square root delta, and then we will get square root delta equal to epsilon. Hence f is continuously uniform. And then for any n element of n, we have function 1 over n minus f0, which is equal to square root 1 over n, which is equal to we factorize the square root n in the modulus 1 over n minus 0. So f is not Lipschitz. So it's already shows that the function square root x is uniformly continuous on 0 to positive infinity, but does not satisfy the Lipschitz condition on 0 to positive infinity.
For question 2, it is given that M1 row 1 and M2 row 2 are two matrix spaces, and then it also given that F, where M1 mapped to M2, is continuous on M1, and F is a closed subset of M2. The question asks us to prove that inverse of capital F is a closed subset of M1. So in order to solve this question, we have to recall that a set is closed if its complement is open. So from the given information, which is F closed subset of M2, it implies that the set difference of M2 and F is open. The set difference here means that it is a set element of A but not in B. So in order to solve this question, we have to show that the set difference of M1 and inverse of capital F is open in M1. So we have to consider the complement of inverse capital F in M1 as written here, which is set difference of M1 and inverse capital F is equals to inverse of set difference M2 and capital F. So since F is closed in M2, so the set difference of M2 and F is open in M2. The function F is continuous by assumption. So the preimage of an open set under a continuous function is open. Therefore, the inverse of set difference M2 and F and capital F is open in M1. Thus it is open in M1, which implies that the inverse of capital F is closed in M1. So it is proven that the inverse of capital F is a closed subset of M1.
Okay, so for question 3, let M1 row 1 and M2 row 2 be two matrix spaces and F maps M1 to M2. Suppose that the preimage of F under F is a closed subset of M1 and F is a closed subset of M2. Prove that F is continuous on M1. So we know that set is closed if and only if its complement is open. So we let U be the complement of F. U is an open set in U2. So we suppose that the preimage of U under F is open in M1 for every open set U in M2. So we fix P in M1 and epsilon greater than 0. We let U be the set of all Y in M2 such that the M1 Y FP less than epsilon. Then U is open, hence the preimage of U under F is open. Hence there exists delta greater than 0 such that X in the preimage of U under F as soon as the M1 Px less than delta. But if X in the preimage of U under F, then Fx in U, so that the M2 Fx Fp less than epsilon. So by definition, F is continuous on M1.
So question for us, if A is closed subset of compact matrix space M row, prove that the matrix space A row is also compact. So firstly, it is compact when the sequence is complete and bounded entirely. So from the information given, since A is closed subset M and M is compact, hence it is bounded, then A is also bounded. A subset of A of a matrix space M row is bounded entirely if, by the definition, for every epsilon greater than 0, there is a finite cover of A by set diameter S less than epsilon. Then diameter S is equal supremum rho xy, where x and y are element of S. So we choose epsilon greater than 0. So every epsilon greater than 0, there exists finitely many points x1, x2 until xn. There is closed subset M such that M closed subset union B sk epsilon over 2, where B xk epsilon over 2 is equal y element of M, where P sk y is less than epsilon over 2. Since A is closed subset M, then A is closed subset union B xk epsilon over 2 intersect A. The diameter of each set B xk epsilon over 2 intersect A is less than epsilon. So for any y and z element of B xk epsilon over 2 intersect A, we have rho y xk is less than epsilon over 2 and rho z xk is less than epsilon over 2. So by using triangle inequality, rho yz is less than and equal rho yxk plus rho zxk. So we calculate them, so less than epsilon over 2 plus epsilon over 2, and then we get epsilon. So the diameter bxk epsilon over 2 intersect A is less than epsilon. So since A is finite cover and diameter S is less than epsilon for every epsilon greater than 0, then A is bounded entirely. To show A is complete, we need to show that for every Cauchy sequence in A converges to a point in A, let Xn be a Cauchy sequence in A. From the definition of Cauchy sequence, for every epsilon greater than 0, there exists integer n such that rho xn xm is less than epsilon, where m and n is greater and equal integer m. So since A is closed subset M and xn is Cauchy sequence in M, it's follow from the completeness of n that xn converges to some point x element of M. To show that x is element of A, we use the fact that A is closed, so it contains all its limit points. That is, if a sequence of points in A converges to a limit x in M, then x must be in A. So since xn is closed subset A and xn is approaching x in M, so we can conclude that x is element of A because A is closed. Therefore, since A is closed, any cosequent xn in A converging to x in M must have x element of A. Thus, A is complete. So, since A is both complete and bounded entirely, it's followed that A is compact. It is proven that if A is a closed subset of compact matrix space M row, then the matrix space A row is also compact. That's all.
For question 5, the question asks us to prove that for every epsilon greater than 0, then exists at least one partition P such that upper sum minus lower sum is less than epsilon. So as we know, Riemann integral is infimum for upper sum is equal to supremum for lower sum. Then since Riemann integral is on every epsilon greater than 0, there exists a partition of interval AB such that upper sum minus lower sum is less than epsilon. Therefore, if F is bounded and closed on interval AB, then there exists real number which is M, which is capital M and small m, such that M less than Fx less than capital M. Then for refining the partition, we let P equal to x0, x1, x2 until xi on interval AB, which the subinterval is xi minus 1 and xi. Then for sum UFP, which is sum of product of length, subinterval and max value, we will got UFP equal to mi, summation of mi multiply with xi minus xi minus 1, and similar with the lower sum LFP, which is equal to summation of mi multiply with xi minus 1. Then we will find the difference of UFP minus LFP by choosing P with sufficient small subinterval. The sum of difference capital M and small m multiply with xi minus xi plus minus 1 over all subinterval can less than epsilon. Then we have shown for every epsilon greater than 0, a partition exists a partition on AB, UFP minus LFP is less than epsilon. Then we complete the